Hello, good afternoon. Welcome to our second meet and greet event, broadcasted live from Prague, from StatsPerform, from our Prague office. My name is Ladislav. I am part of the recruitment team here at StatsPerform, and I will be hosting you today. And I'm not alone, actually, here on the stream. There is also my colleague Alex, Alex Duben. Alex, can you hear us?
Yes, hello.
Thank you very much. How are you today?
I'm pretty good. I'm looking forward for presenting some interesting technologies today.
Perfect. Thank you very much. So why we are organizing such events? We are organizing these meet and greets for you to have a little bit more insight to what exciting features, what exciting things we are doing today. We are doing here at StatsPerform. As I mentioned, this is our second meet and greet event, and we want to take also this opportunity to present you our open roles. Usually, it is my pleasure to welcome our guest speaker, Alex Duben. Alex works at StatsPerform as an engineering manager. He is managing Prague-based data engineering team, and he will be running his presentation today about Redshift streaming ingestion. So, Alex, now it is your turn.
Right. Thank you very much, Ladia. As Ladia said, my name is Alexander Duben. I work as engineering manager at a team that we call data platform engineering. What I prepared for you today is a bit more technical topic. It's the story is about how we used a piece of technology called Redshift streaming ingestion over past year to deliver a new product within the company, and it's pretty new feature. So I think there's not a lot of information out there, so I hope it will be interesting to you, and you will learn something, maybe start to think about how you could use this as well in your workloads that you work on. So let's get into that, but before we do it, I think it is important to also give you a bit of context, basically what's StatsPerform about, and why did we even have to work on this project. So really, I'm going to make a pretty short summary. StatsPerform has quite a long history. It goes back almost 30 years now, but I would not be surprised if not a lot of you know StatsPerform as a name. The reason is very simple. It's mainly caused by the fact that we sell products to other companies, not really the end user, but actually you might have been using our products without even knowing that, especially if you're a sports fan, because the backbone of our business is sports data collection. We are pretty big in that. I would say we are one of the biggest companies that operate across the whole world, and sports data collection is our main product that we basically can deliver. And really, it is successful because the biggest players in the industry are using our data. So companies like Facebook, Apple, Google, all of these are getting sports data from us. Of course, sports is a massive fan engager. So all of these companies are really interested in our data. This data in the past was, of course, mostly collected manually, but with how the technologies were developed and with the company investing into tech, we started automatizing this process as much as possible. So it's still not fully automatic, but it's a mixture of both, and very nice examples of our data maybe being present in your lives. Whenever you Google a result of your favorite football team, there's going to be this nice table that's going to pop up. It's of course rendered by Google, but the data that it is populated with is for sure from us, and Google is hitting our API somewhere in the backend. Another example, if you're using Apple and their voice assistant Siri, if you ask Siri who won the last year's championship, for sure Siri is going to hit our backend and get the data from us. So you might have been using our data via these basically daily features without even knowing. So really we can say that our products are used by millions of people across the world, because we don't only collect few sports, we actually collect pretty much everything you can imagine. And of course, some sports are more popular than others. So we focus a lot on football, tennis, basketball, and cricket, but we pretty much have something for any sport that you can imagine. So that's the data, but of course we don't only produce the data and sell that, we also build products on top of the data. It makes sense. You own the data pretty much fully from the creation. It makes sense to build your own products on top of that. And one of these products is called Optavision, and that's the product basically that we were working at with other teams. It's a pretty big product. It's not just our data platform team, but also other teams across the company. And basically, we were tasked to deliver and enable this product from scratch pretty much over the last year. And what this product is, I'm going to definitely explain, but I think the best first step to do this is to just show you an advertisement video that we typically show for the product. It is quite, let's say, cryptic at times, so you might be confused, but don't worry, I'm going to explain and summarize what you can see in the video. So let's watch it first. All right, so now to kind of summarize it. So if nothing else, I'm sure you got an understanding that this product is football based, and that's the case for sure. And if we can kind of put it in words, Optavision is a data feed, which basically offers you a very rich data set which is being generated as the football match is running, and which offers you basically not just the actual information from the match, like positional information in time and even data, but also deeper insights into the statistics of the match. So really, it's a rich feed that you can use to basically enhance your football experience, but not just the experience, but actually the knowledge about the match you have. So the kind of plots that you could see there, that was basically a representation of the input data on top of which this product is built on. We generate this data ourselves, and it's basically three main types of data that are used as inputs into this pipeline. So first thing that we can talk about is the tracking data. Tracking data is really just positional information of the players and the ball in time during the match. This can be collected via multiple approaches. The first approach that we use here is something called in-venue tracking collection. This means that typically you have a set of cameras present in the stadium directly, or set of sensors that basically generate the tracking data which contain the positional information that you need. Of course, this is the most accurate way of doing this, but you can imagine this way, you really need to be present in all the stadiums in the world, ideally, if you really want to have this as a global product. So that's why we kind of moved away from this social network. Not moved away, we still use it, but we actually start working on alternative way of collecting tracking data, and that's really taking traditional media feed from the match. So really the same video you would see in the TV, for example, when you're watching a match, and run that through our own custom-made computer vision-based solution, which generates the tracking data in a similar format as the in-menu tracking would. So this is where we invested quite heavily. This pipeline is pretty much fully autonomous, and there's a lot of hardcore engineering and science behind this. So these are the tracking data sources, but there's also a third source that you can see on the picture as well. It's here, it's called event data. And I mentioned that the sports data that we are able to generate is still being collected manually as well as automatically. And this is the part which is still necessary to be collected manually. So this is done by our employees. What kind of data this is? It's basically anything interesting that happens in the match. So passes, shots on goals, corner kicks, fouls, and so on. These events, it's still pretty hard to collect automatically. Of course, we'd love to get there, and we are working on that actively. But for this product, this data set, it's still collected manually. But either way, even if it's done manually, there's still a lot of interesting technology behind it, because you need to build the collection tools for the operators and so on. So there's quite a lot of tech behind that. So now what happens with this data? I'm sure you understand that each of these data sets gives you different insight into what is happening in the match. So ideally, we would love to somehow leverage the information from all of these. And this typically means that you need to somehow fuse the data together to create one unified data set. And this is what can be seen basically on the timeline or on the representation of the product pipeline. So we have this real-time QA step in the middle, which is basically synchronizing these data sets against each other, cleaning them up, and so on. And this is partially done automatically, but you still need a human in the process to verify and do this with high quality. So once we have the clean data set, finally it gets fed into our machine learning models, which give you those deeper insights into the data that you would not necessarily get just by watching the game, or the positional data you would get from that. So these machine learning models are our own. We have our own in-house data science teams that work on these, and those generate these interesting statistics like detection of line-breaking passes. There's a bunch more on this slide. Detection of pressure like during the match by each team. We can also basically get insight into efficiency of each player when it comes to passes and shots. And there's really a bunch more that we enable by the power of machine learning. So at the end, you really get pretty much the positional information as well as the event information from the match. So you can kind of reconstruct what was happening during the whole event, as well as additional interesting statistics. So you can probably imagine there's a lot of potential with such data feed, and we have customers from all kinds of domains, from media who can use this to drive fan engagement, to betting, to the teams themselves who can really use these deeper insights to maybe optimize how they play, or at least understand what is happening during the match. And so that's the product. There's one interesting slide here. This is basically an example of one of the tooling that we had to build to enable human operators to work with the data. This tool is used for the dataset cleanup and synchronization that I mentioned. This is how it looks. So you see the video, you have the tracking data plotted in there as well, and we had to build this from scratch in-house as well. So this is the product. And now, what was the part of my team in this? So here we have a simplified diagram that kind of shows the definition of the problem that we were tasked to solve. And you can see the data platform is in the center of all of this. And that's not a coincidence. Our data platform basically serves as kind of a central spot for all kinds of data sources within the company. And we then provide not only access, but also analytical capabilities to other teams within the company who then use it to build the products. And that's basically how it is set up. So we are an internal platform team, you can say. And this product was basically one of the products that we had to enable. And interestingly enough, we didn't have solution in place that will be suitable for that until then. So it seems quite simple, actually. Like there's not a lot of arrows. You can see that you have those three data sources that I mentioned ingested into the platform. Then you have the operations who need to be able to basically access the data and produce the clean data set, which is then fed into the machine learning models. And finally, the finished feed is then somehow provided to the customer via some API, but the details don't really matter here. It might seem very simple, but if you take a look at the actual requirements, you will understand why it was a bit of a challenge to get there. So first thing, the amount of data, it's quite large. So just to give you a scale, one match worth of this tracking data, it doesn't matter if it's in-venue or this CV-based data, is about 2 gigabytes. It still might not seem that much, but this product should really be a global product, which means we would love to process as many leagues in the world as possible. So then you don't need to count with scaling up to thousands of games across the world. And once we really want to enable that, we need to count with large amounts of data. And another thing that makes this quite hard is that it's spot. So you would, in ideal case, would be able to do this whole thing as close to real time as possible as the game is running, because everybody is interested in these insights basically live during the match. Of course, it's interesting after the game as well, but if you can deliver it real time, it's going to have much more potential. So we should do this whole cycle ideally live and real time. Real time might be a bit confusing here. It's for sure not real time in the meaning that we are talking about milliseconds here. The real time in this context is real time from, let's say, media perspective. I'm sure you know that everything that runs live in TV is typically delayed by a certain amount. And that's what we are trying to achieve here as well. So for us, the deadline for processing was 60 seconds. So we had to be able to ingest the data, allow the access to the data, provide the analytical capabilities all within 60 seconds. So that's the problem definition. Now, a bit more about how our data platform looks like under the hood. This is the most simplified architecture diagram I could create. It makes sense here because we really don't care about the details here. The main building blocks of our data platform are Kafka for the live data that we need to be able to ingest, and Redshift as the main warehouse for the historical data. All of this is running in cloud. Our cloud of choice is AWS. And of course, you cannot really build a data platform just with Kafka and Redshift. You need some form of orchestration to basically take care of the data flows. And we heavily use serverless stack for that, which is Lambda functions and all the other services typically used with Lambda functions. And you can see basically the most basic flow is ingesting the live data, providing some users that want to access live data the access to them, as well as historiating the data to our warehouse. We might also have some historical data sources which are not really running live, which also should be able to ingest into the warehouse. And then you have, of course, users that want to access the warehouse and run their analytic queries against the whole history of data that we might have. So this is the most basic flow. And in this situation, we are basically talking about the flow where the tracking data is coming in live. So it will be coming into the Kafka cluster, and we somehow want to enable the access to that live data as it is coming. So if we don't kind of go into the territory of basically directly processing the stream, typically what we would be doing with such tasks is to get it to the Redshift cluster somehow. And traditional approaches that we also used in the past would be maybe these two. So first one is getting the data into intermediate S3 bucket, and by using the built-in copy command within Redshift, copying the data into the cluster. This is quite performant. The copy command has really high throughput. You can copy big chunks of data into the cluster. The issue is with this that the latency is not enough in this situation. We would not be able to get under those 60 seconds that I mentioned. Another approach that is also possible is doing it very simply. Basically have some intermediate consumer between Kafka and Redshift. In past use cases, we might be using Lambda function. That's basically just ingesting data and inserting it directly into the cluster. This works well. You can get to nice latency here, but the throughput here is the problem because typically these inserts are going through the leader node within the Redshift cluster, which has limitations and kind of serves as a bottleneck, and you cannot really use the full parallel computation power of the cluster. So this was for sure not the way to go. None of these solutions was kind of serving our needs. So what did we do? So we did our own research, and basically the main runner-ups, I would say, would be to really just kind of go and process the stream live with some specialized tool, like for example Apache Flink. But there was a problem with that approach because especially the machine learning models that are accessing the data, those are typically set up in a way where they access our Redshift, and they work with SQL commands, into traditional SQL commands to do the analytics they need to train the models and do the inference and so on. So it would be a lot of extra infrastructure, a lot of extra setup, basically introducing completely new technology. But we found basically a thing called Redshift streaming ingestion, and that's basically the top is the point of this session. And this built-in functionality of Redshift is actually pretty new. It was released only last year, I think, publicly. It is a reaction of Redshift and AWS to this need. It is a service that allows you to very easily set up a connection between the Redshift cluster and your streaming solution. Right now it supports Kinesis and Kafka. So we don't need anything else since we already been using Kafka. And once you set up the connection, you are able to ingest the data with high throughput and low latency. So that's basically the perfect solution to what we needed. And it is new, so we did not really trust it that much from the beginning, but it sounded really great. So we really started playing with that, and in the end, we decided to go with it and basically move it to production and use it for enabling this pipeline that I've described. So this picture kind of shows how it works internally. We basically create a connection, and then the data gets stored in materials view. So that's it. You don't need any extra infrastructure or nothing like that. Basically, the data is then continually being inserted into your view, and you can directly run analytical queries against the view as if it was a normal table within your cluster. So it pretty much does very similar thing to what a stream processing might do at the end. A bit more about the setup. I mentioned it's very easy to set up, and it's really very easy. It's just three main steps that you have to do. So first, you have to create an IAM role. It's basically a permission that allows your cluster to access the stream. In this situation, it's an example for Kafka, since we are not using Kinesis for this. And once you have the IAM role, you create an external schema within the Redshift cluster, which is basically coupled with your streaming or with your stream cluster. So you pass in the role, and you're pretty much done there. The connection is set up. And the last thing we have to do is to create that materials view as the landing area for the data that I mentioned. And an example how this might look is this. Interestingly, I guess you can see that all of these are SQL commands. So it is not possible to set this up via Terraform or the AWS console yet. You really have to connect into a cluster and really run it as a SQL load. This example of the materials view is pretty much the most basic view definition with full amount of data that you have available. So you can see it's a bunch of Kafka metadata, and then you have the payload as one of the columns basically available. What might be also interesting is the from part of the query, basically how you target specific topic. So you basically target it via dot from the external schema that we created in the previous step. So in the end, basically you have pretty much a virtual table per topic for your whole Kafka cluster available once you create the external schema. Finally, to get the data actually populated in this view, you have to refresh it as any other materials view. And this is the command. Once this is done, you can basically go and start running your selects against the data. The output might look like this. I'm sorry I couldn't fit the whole thing in, but I think this gives you idea how that looks like. You might be thinking, well, how is the data actually stored? And like you have it only in one column. For this, Redshift has a special data type called super data type. It's basically a custom-made data type to store semi-structured data and files, for example. In this situation, our payloads are JSON, so you basically just dump JSON into the column, and it also supports some other ones like XML files and a bunch of others. So it's really a place to store not fully structured data in the usual sense. You might think, well, that's okay, we have the data there, but now we cannot really use it since it's really wrapped in the JSON structure. That's correct, but actually there are ways how to work with the data directly. Redshift has a feature called particle language. It's also known as dot notation, and it basically offers you to target data fields even within this superstructure as you would basically with any other tool that can work with JSON. So you really via dot you can address the select directly to retrieve a piece of the payload. So this is how such a select could look like on the bottom. Of course, you don't really have to define the primary materials view this way. You could already have some transformation here. It is possible, but I would strongly advise against that. Why? We're going to definitely comment a bit later. So like I would really strongly suggest using this basic data dump as the primary data landing view. So that's the basic flow. Now, how did we use it in our production then? So there are two things to solve. First thing was how we can achieve the low latency. So if you think about it, it's pretty clear. It's all about the materials you refresh, because until you refresh, you don't get any updates automatically. You need to refresh the view so it's populated with the latest data. So to achieve the lowest latency possible, you pretty much have to keep these refreshes as fast as possible, which means the data slices will be as small as possible and all the ingestion will be fast this way. So how to achieve this? There's several options at hand. The AWS documentation around this streaming ingestion suggests, for example, using auto refresh setup. So there is a built-in feature that enables you to just turn it on, and it should make sure that the data is getting ingested as fast as possible as they come. But we tried it. It was not working that great. You don't really have any control over that once you turn it on. And really, sometimes Redshift would decide to deprioritize these refreshes and introduce additional latency. Sometimes it will just get stuck and we didn't know why. So we decided it's not the way to go, and we have to have more control over these refreshes. So we built our own orchestration solution to do that. And this orchestration solution was tasked with basically keeping the refreshes as fast as possible, but also making sure that the cluster does not get overloaded, because it can happen quite easily with this. If you start throwing the refreshes at the cluster too fast, it might not handle it based on how many resources you have, of course. So this was the basic flow. We had the raw materials view available. Why we chosen the raw materials view? It's very simple. You cannot really know what the producers might send into the stream. If you introduce some transformation already in the first step where you ingest the data, it might happen that the incoming data is not compatible with that. In that case, the streaming ingestion will just fail, and it's actually quite hard to kind of monitor this actively and debug it right away. So we kind of went the way of like the maximal throughput. We would allow everything to get in, and we will address it basically later at a later stage. So that's why I would really use that, because if you define, for example, data types that you expect, it will fail for sure. And in that case, you have to either get the wrong event out of the stream somehow, it might be complicated, or fix your view definition, and that means dropping it and losing the data which is stored there typically. So how we address the other part of this, and basically, apart from latency, we also had to make sure that the operation teams and the machine learning models can access the data somehow in an optimal manner. We simply went and defined like subsequent traditional ETL process that would be just taking the ingested data from the materials view, which are not really structured. They are just dumped there, and introduce a structure. So it would be traditional ETL process where you get the data, you transform it, and insert it into another traditional table within the Redshift. We chose traditional table instead of another materials view because, as I said, it might happen that the primary materials view might need to be changed. In that case, you would have to drop the whole chain of those views, and you will lose the data which are stored there historically. So that's why, at least in one of these layers, we wanted to have traditional table, which would not really lose the data even if the views need to be changed. And that's basically it. You have full power over these transformations then, and you typically optimize the structure depending on how the data is read. So it does not have to be one, it can be multiple levels of transformation or several parallel flows, of course, and each of these can be in different format depending on what the actual users are interested in, and you can optimize it by setting up correct sort keys and distribution keys and so on, but it's kind of an outside of the context of the Redshift streaming ingestion that's just normal data processing. And we, of course, had to somehow keep this process orchestrated as well. You need to keep it updated with the incoming live data. And we figured, well, we already have an orchestration solution for orchestrating the refreshes. Why not to use it also for these inserts and transformations along the way? So we did that, and we pretty much built the pipeline this way. And we still use it this way in production right now. Maybe to give you more information about the orchestration solution that we used, we built it our own. You might be surprised by that. Why didn't we use something working out of the box like Airflow? We were not using Airflow for anything else at the time. It was not part of our tech stack. And actually, it seemed like it should be doable by something like normally available within the cloud. We went with a Lambda solution. So this Lambda is triggered by configurable cron generator. So you can have different rates for each stream that you are ingesting, and the Lambda is making sure that the rates are basically respected, as well as it's making sure that the cluster can handle that many refreshes and it would not overload it. One big advantage of building your own orchestration system in this situation, instead of using, for example, that auto refresh or having like scheduled SQL set up for the refreshes, is that you can monitor this really deeply. So it's Lambda, you can pretty much create any monitoring you might imagine. And yeah, we built ELK based monitoring dashboards on top of this, and it really gave us a lot of insight into the dynamics of the system, especially when we were tuning it for the high throughput and low latency, because it was not a smooth ride from the get-go. We had to play with it a bit, and basically this monitoring was the main thing that enabled us to understand what is happening within the cluster. So long story short, it was a success, of course, otherwise I wouldn't be presenting it here. Before we get to the actual numbers that we achieved, I think it's important to also mention the actual data flows that we are handling. So right now, we typically process on average 60 games per day. This doesn't mean just like 60 raw data streams from, for example, the CB tracking generator, but it is those full 60 cycles, including the data fusing and basically cleanup and the machine learning inference. So basically 60 full cycles of games can be done. Right now, the limitation is not the technology, it's typically the manual part of the process, so the operations people who are working on these data sets. At times, the amount of data that we have to ingest is about 40 of those tracking data streams processed in parallel. So the parallel data flows are quite large, and we process this with 4 nodes Redshift cluster with XL plus class. You can see the load when it comes to CPU utilization on this slide. What is interesting is that all the compute nodes are utilized more than leader, and this is great because in this situation it is clear that this feature will enable you to basically utilize the full parallel powers of the cluster, because it is not going through the leader node. The compute nodes are directly working on these loads and ingesting the data. So there is a lot of advantages, and you can see that the utilization looks healthy, and we are not really hitting any limitations here. So what are the numbers then? So this is, I think, the most important result of this setup. These are 4 different entities you can see here, and the difference is basically the subsequent transformations that I mentioned that we have in place. So each of these entities might be coming from the same raw materials view, and you simply just transform it differently at the end. And the end-to-end flow of the data from really getting into the Kafka and being available for selects, that's the time that we have basically plotted here. And as you can see, even for like the more complex entity, which might have a more complicated transformation, we are on average at 15 seconds mark, which is well below the 60 seconds deadline that we basically have for processing this data. So it really means that whenever a new data comes, within 15 seconds, sometimes even faster for less processed data, you can already run analytical queries against that. This is very surprising to me. Really, I kind of think that it brings the, let's say, OLAP world closer to the OLTP. Of course, it's still not the same with OLTP databases. You can go much lower when it comes to ingestion. But with OLTP databases, you would not have the same analytic powers as with Redshift, for example. So if really your timescale where you want to process your live data is in seconds, you really don't need any specialized stream processing for that. You can just ingest it via this into your Redshift cluster and run the live analytical workloads as if it was the historical workloads, which once again deduplicates and despecializes your use cases, and it's basically just one use case, and all the subsequent data analytical pipelines just work as one. So this is another view on the performance. It's an example of the monitoring solution that we built on top of the orchestrator. It's basically just plotting the Lambda runtimes, which are correlated to how much time the refreshes take, because it waits until the refresh is done. And you can see really the refreshes are around 6 seconds on average. Now, bit about scaling of this solution. So I mentioned we had to be able to basically scale this up to thousands of games. And the magic of this is really that it scales itself pretty much. It is just plain Kafka and plain Redshift that you're using. There's nothing any special in there. And these services pretty much scale themselves, and you don't really need to somehow take care of it in a complicated manner. Of course, there are still some things you have to take care of and keep an eye on. If you ran out of CPU utilization on your Redshift cluster, of course, this ingestion will get slower as well. So as long as you have enough resources on the cluster, there should be no trouble basically scaling this up for your needs. Right now, as I said, we cover 60 games per day. At peaks, the data rates are about 20 megabytes per second incoming, and this is really nowhere near the limits of Kafka or even the Redshift. So there is room to grow, and of course you have to keep in mind there might be other infrastructure that might suffer because of that, and that's the case with us. Like, we have bottlenecks in our pipeline, but it's not Kafka and it's not Redshift, so we can definitely ingest even more data in the future through this solution. What's also pretty cool is that as I said, it's using the compute nodes, which means it's fully parallelized flows. Typically, if you add another parallel stream to be ingested, it doesn't really affect others because it runs in parallel. Yeah, there's not really a big challenge to scale this solution up. What's interesting is, and might be interesting to some, based on our experiments, we think that since like the refreshes are nothing else than basically selecting a block of data within some storage, which kind of mirrors the Kafka retention window, which is basically the backend of Kafka, where Kafka keeps the data. So we think that if the retention window is larger, these scans will have to be longer as well, which means the refreshes might need to be a bit longer. So if you will be somehow tuning this solution, it might be worth taking a look at the Kafka retention window, but we don't have any verification. We did not really play with that. Our Kafka retention window is fixed, so we just think that might be the case. Finally, some takeaways that we took from the tuning. So first, as I mentioned, the orchestration needs to be fast, but you need to make sure that you don't overload the cluster. And one of the biggest things that we had to do was fully serialize the refreshes. So right now, we don't allow parallel refreshes being run. We wait until the previous refresh is done, until we trigger another one for a given stream, of course. You can have parallel streams refresh regardless of each other. Another thing that we had to deal with was the fact that the data that we are basically updating live is also used quite heavily at the same time. And of course, you have a concurrency there. And we were getting deadlocks in the first stages. We solved it by turning on a feature called snapshot isolation on Redshift, which basically changes how the internal multi-signal logic works when it comes to accessing data. You can just turn it for a specific table if you want. And basically, this makes sure that whenever a consumer wants to access the data, it provides a snapshot of the table instead of giving access to the table where you need to really claim a mutex or something like that. So yes, by giving snapshots to the consumers, it might mean the latency might jump up a bit, but actually we did not see any negative effect of this, and it actually solved all the concurrency issues that we had. So snapshot isolation is good to keep in mind for such cases. And yeah, the final takeaway, of course, you always need to keep in mind that how your data is accessed and possibly transform the data in a way where it is optimal with regards to how the data will be accessed. So you need to have proper sort keys, proper distribution keys, and basically the table structure needs to make sense for the user. And that's pretty much it. So it was really a success on our end. We achieved what we wanted. It is performing really great for this Optavision product, but there is much more potential for this feature. So we realized it's really good, and actually we went ahead and switched over like all the data streams that we have in Kafka to be historiated via streaming ingestion into Redshift this way. So right now we are running this for more than 100 topics. Of course, not all of them are time sensitive. You don't need low latency there. For these topics, you can just refresh them less frequently, and it means less needed processing power, and it works really great. So we use it now to basically dump all the Kafka data into our Redshift. With this, we also we are working on a feature that we would like to basically roll out to our development teams. It's called Kafka Replay, and we would love to enable engineers to basically redrive any streamed data back into the Kafka as it was in the past. And we're going to use basically the Redshift as a backend for this. And it has a lot of potential use cases, testing, debugging, maybe enabling even new products, since you can really have this data time machine available for the streams. So that's it from me. I hope you enjoyed it. I hope you learned something new. And now we will move over to the Q&A. All right, so first question is why Kafka was chosen. The answer is very simple. We use Kafka historically in our stack, and it was already there, so we did not really have any other option. In AWS, actually, you don't have that many options if you want to use the managed services, which we want. We are a smaller team. We don't want to take care of infrastructure that can be handled by the cloud itself. So really, the main options here would be Kinesis or Kafka. We use Kinesis as well, but it has its limitations. Kafka really is more robust solution, in my opinion. You have more power how you want to manage it and set it up. For example, it is quite troublesome to trigger cross-account consumers from Kinesis. I think they might have added it recently, but I know it was the case in recent past. So yeah, the Kafka is basically a streaming solution of choice, and since there's a lot of depending on it already, he did not really think about changing it, and it was basically just precondition of this problem. We knew we have Kafka. We knew we want to somehow ingest the data from there.
Is there something, Alex, from your end, what you want to share with attendees?
Well, I really enjoyed the presentation. It was a pleasure to prepare it for you. I hope that you will take some knowledge out of this, maybe a tip for your future project. And that's pretty much it. Thank you for the attention, and have a nice rest of the day.